Welcome to this video. In this video I'm going to attempt to give you an intuitive explanation as to why integration in calculus works. Now this video is intended for calculus students, so 17, 18-year-olds, and it is going to be an intuitive explanation as to why integration works rather than a fully rigorous explanation as to why integration works. There is a branch of mathematics called real analysis that is the rigorous basis for single variable calculus. In real analysis, students study a much more rigorous explanation of why integration works. That is not the explanation that I am going to give here. Instead, this is intended for calculus students who have not studied real analysis but would like some sort of intuitive explanation as to why integration is anti-differentiation, why the fundamental theorem of calculus holds true. So let's start by actually writing down the fundamental theorem of calculus, and then we'll try and come up with an intuitive explanation as to why it works. So let's say that we have some function, y is equal to a function of x, f of x, and let's draw a graph for this. So this is the y-axis, and this is the x-axis, so I'll just label them up. And let's plot our function. So of course, f of x takes all values on the x-axis, all real numbers, and maps them onto another real number on the y-axis. So let's say that our function might look something like this. So this is f of x, the graph of f of x. And now let's say that we have 2 points. So let's say one point is little a, and the other point over here is little b, and we now want to know what is the area under our graph between the points a and b. So we want to know what this area that I've coloured in here is. And of course that is the central question of integration. So the area between a and b of f of x is the integral of f of x dx between a and b. That's what the integral is defined to be. It's the area underneath the curve between the 2 points. Now, the fundamental theorem of calculus states that this is equal to the antiderivative of f of x, which I'll call capital F, which is conventional notation, evaluated at the end point b, subtract the antiderivative of f, capital F, evaluated at a. So I'll stress again, this capital F is the antiderivative, and this is the fundamental theorem of calculus, which is often abbreviated down to the FTC for short. And this is quite incredible. This says that if we want to know the area under the curve f of x between 2 points a and b, what we need to do is anti-differentiate. So we need to find a function capital F of x such that when you differentiate it, you get little f of x. So I'll just write that down explicitly over here. So you want to find a function capital F of x such that if you differentiate it with respect to x, you end up with our little function f of x, and that is anti-differentiation. So I'm assuming obviously that you understand what differentiation is, and that you can now look for a function function capital F of x such that when you differentiate it, you get your original function. So we want to attempt to explain why this is true. Why is it that the area under the curve is equal to the antiderivative evaluated at the end point b, take away the antiderivative evaluated at the start point a? So here comes the intuitive explanation. I want you to imagine creating a new function, and we'll call this new function capital A of x. And the reason I'm calling it that is because it's going to stand for area as a function of x. Now, I'm going to draw this as a graph, this function a of x, and it's going to take all the points on our x-axis here, and it's going to map them onto another real number on the y-axis here. And I want this function to be equal to 0 at a. So that's the first requirement. I want it to go through this point here. I want it to be 0 at a. And the way I'm going... Oh, whoops, that's not what I want. I want it, if you evaluate it at little a, for it to equal 0. Now, here comes the crux of it all. The way I'm going to define this function is I want it to be the cumulative area function as you progress along the x-axis for my function little f of x. So I want you to go along all of these points and I want you to ascribe the value of the area under the curve f of x from the point little a onwards. I want it to be a cumulative area function. So let me make that more clear. So if we go to, let's say, and I'll get a different colour. Let's say we go to another point, let's call it c here. And we want to know what is the value of this new function that I've defined at c. Well, I want it to take the value of the area under the curve f of x from a to c. So I want it to have the value of all of this bit of area here. So what I am saying is we are going to create this function a of x, and it is going to map all of the values on the x-axis onto what the cumulative area under the curve f of x is from the point a onwards. So if we went to this point c, the value of this function a of x would be work out what the area under the curve f of x from a to c is. So work out what this is, this area here is, and then plot that value as the value of the function a of x. So maybe if I was to plot it, it would be up here like that. And all of the points in between a and c, they'd have the same definition. So if I went to a point here, the value of a evaluated at that point would be the amount of area under the curve f of x between a and that point in between. So it would be this area here. So this area function might look something like this, etc. And it's getting bigger because the cumulative area under the curve f of x is gradually getting bigger as we go past the point A. So I hope you understand that, and I hope you understand why that's going to be so important, because if we were to be able to find this function and we evaluated it at the point B, well, that would be the cumulative area under the curve f of x from A to B, i.e. it would be the value of this thing that we want to find, the integral of f of x between A and B. So if we could build this function, all we'd have to do is then evaluate it at B, and it would tell us the value of our integral here. Now, of course, what I have said so far tells us how to build the function if you're going this way, if you're going up from A. All you have to do is work out what the area is from your point A to your point x underneath f of x, and the function is the cumulative area as you're going along, and it's getting bigger and bigger. What about going downwards? Well, it's obvious what we should do. We just then need to subtract the area. We need to go negative. So if you were to go to a point over here, and again I'll draw this on. So let's say we were to go to a point D over here. Well, for this area function evaluated at D, what we'd do is we'd say how much area is under the curve between our point D and A, and we count all of this as negative because you're going the opposite way now. You're going this way, obviously, whereas before we were going this way. So the cumulative area function is going to go negative now, so we're going to subtract this area off from 0, and it will therefore be negative. So if we were to continue plotting this function, it would go down here, like so. So I hope you understand what I'm saying. I want to create a cumulative area function, and I want to centre it around my point little a. And the reason I've done that is because obviously we're trying to work out the integral of f of x from a to b, so it's just convenient to centre it around a and say that at a we're going to define it to be 0, and then onwards to the right we're going to make it get bigger and bigger and bigger, and onwards to the left we're going to get it to go smaller and smaller and smaller, and it will decrease by the size of the area under the curve. So this is a cumulative area function. And if we evaluate it at b, we will get the value of the area under the curve between a and b of f of x. So you might say, well, that's a brilliant idea. Yes, it would solve our problem if we could find this cumulative area function, but how on earth are we going to find this cumulative area function? Because it seems a very complicated thing to find. Well, the way in which you find this is by considering what would the derivative of this area function be, and you're probably already suspecting what the answer to that is going to be. So let's just ponder it for a moment. So let's imagine taking the derivative. So we'll go over, I'm trying to find some good space to use, we'll go down here. So if we consider taking the derivative of this area function that I've just defined, this cumulative area function, with respect to x, well, we know what the derivative is. We have some intuition about what the derivative is. It's this infinitesimal gradient, effectively, is the intuition, the informal intuition, the unrigorous intuition behind differentiation. So let's just go down a little bit. So if we've got a little bit of our curve here, so let's say this is a little part of this cumulative area function. If we were to take a point, let's say this is x here, and we were to consider what is the derivative of a at that point with respect to x, then the informal intuition for what we're doing is we're going forward a tiny little amount, dx, an infinitesimal amount. We're seeing how much does a increase over that tiny little amount. So here is that tiny little change here. So we're imagining drawing a tiny little infinitesimal triangle, smaller than all numbers in the world, a triangle here. And we're saying we're going forward by this infinitesimal amount, and of course you go up by an infinitesimal amount dA here. And then of course the gradient is then that tiny little infinitesimal change dA over dx. But let's just consider what actually would dA be. So if you go forward a tiny little amount, how much would the cumulative area function change? Well, let's go back to our picture up here. So of course the area function increases by the cumulative area, by the amount of area that would increase if you go forward dx. So let me elucidate that further. So let's say here is our point x that we had on this picture here. So let's relabel up the point that we previously called c. Let's call that x now. And we're now going forward a tiny little amount here. So this is the tiny little dx, and we're asking how much would a go up? How much would that tiny little change in a be? Well, of course, what we need to think about is how much would the area under the curve f of x increase if we go forward by a tiny little amount dx. Well, if dx was truly infinitesimal, if you make it absolutely tiny, then it becomes very, very simple, because imagine making this little shape here, this little piece of area, making the dx smaller and smaller and smaller. Hopefully you can appreciate that if the change in x becomes absolutely tiny, then the complicated bit up here becomes very simple. You see, the complicated thing about finding the area here is that all of this bit's lovely, but up here it becomes complicated. However, because it's the function, the border up here is the function. However, if the change in x becomes absolutely tiny, then this is going to become more and more like a rectangle, effectively, because if you're only going forward by an infinitesimal amount, then the value up here pretty much becomes constant. So what I'm saying is that this area effectively becomes a tiny little rectangle as the change in x becomes tiny. And of course the height of that rectangle is just going to be f evaluated at x. So that would mean that that area of that rectangle would be f of x times the tiny little change dx. So f of x is the height of the rectangle, and dx is the tiny little width of the rectangle here. So let me explain what we're doing again, because it's really important that you understand this. So we are trying to figure out what the derivative of our cumulative area function that we're trying to find would be. And we're saying, well, the derivative is if you go forward an infinitesimal amount, how much does the area, the y variable, change here, and take that change and divide it by the tiny change x to get the gradient of the triangle. Now, in order to find that then, we need to know what is this tiny little change in area for a tiny little change dx. Well, of course, the way we define this is it's the cumulative area function, so it is going to increase by how much the area under the curve from a to your new point x plus dx is going to increase from the old area from a to just x. And of course that's going to be this tiny little rectangle increase here. So we're going forward a tiny little amount dx. The height of the rectangle is going to be f of x, and I've convinced you, hopefully, that you don't need to worry about this upper border here being really complicated, because if we're making the change in x absolutely tiny, then this is going to become effectively constant up here. It's going to just take the value of f of x, and therefore it's going to gradually converge on being a rectangle as you make the change smaller and smaller. So that tiny little change in area will become f of x times dx as dx becomes infinitesimal. So we can now say that dA would be f of x times dx. And therefore, we can say that the derivative, the gradient, of our cumulative area function would be equal to f of x. And that's the genius of this. There is why reversing differentiation is how we integrate. Because now, if we want to find our cumulative area function a, what we need to do is find a function whose derivative is f of x. So we need to anti-differentiate f of x. We have a differential equation here, a really simple differential equation. So all we now need to do is anti-differentiate f of x. So presuming we know a lot about differentiation and that this function is something nice, then we stand a good chance of being able to find the antiderivative of the function little f of x. We will call this capital F of x. So now, if you know anything about solving differential equations, you will know, of course, that there is not just one solution. We cannot just write down that the area function a of x is equal to the antiderivative capital F of x, because of course this antiderivative is just one of a collection of antiderivatives of the function little f of x. We always end up with that constant plus c here, because if you were to differentiate, if it's the case that if you differentiate this you end up with little f of x, then if you take any variant of this plus some constants and differentiate that, you'll also end up with little f of x. You end up with a whole collection of possible solutions. Which one is right? Well, we're bounded by this condition. We made the condition that we wanted the area function evaluated at little a to be equal to 0, and that sets what the constant function is equal to. Because the reality is that this collection of solutions, all they are is the same solution plus a constant term. So they're actually just, imagine this function, but move it up, translate it up by a certain plus c. So we just have to pick the correct one that's going to, at a, give the value 0. So now we just feed this into the equation. We want a at little a to be equal to 0, but of course that's going to be equal to f, capital F evaluated at a plus c, so we want this to be equal to 0, and that of course means that c has to be equal to negative this capital function f evaluated at a. So that means that we end up with our area function evaluated at x is going to be capital F of x minus whatever this function is evaluated at a. So there we have it. There is our cumulative area function. It's the antiderivative. You find me an antiderivative of this function, evaluate it at a, subtract that value off, and here is the cumulative area function that I wanted that is going to go through 0 at the value a. And now we can do the final thing, which is evaluate this at b, and we have the answer to our question. So if we evaluate this now at b, that will give us the value of our integral that we wanted over here, and of course that's going to be equal to f evaluated at b minus f evaluated at a. And there you have it. There is the explanation as to why the integral of little f of x dx evaluated between a and b is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. And this will work for whichever antiderivative you find. So you can find any antiderivative, any one of these, it will work, because you're always going to subtract off this bit. So it will always work. So you don't need to worry about which antiderivative capital F of x was originally. So let me just give that explanation again. I'm going to summarise it again just to make sure that you understand. So this video is to try and give an informal intuition as to why the fundamental theorem of calculus works for people who are studying calculus for the first time, so 17 and 18-year-olds. If you go on and do a maths degree, you will learn a branch of mathematics called real analysis, which is the rigorous theory of calculus, where they will give you a much more rigorous explanation as to why integration works, why the fundamental theorem of calculus holds true. This is an informal intuition, not a rigorous explanation. So let's go over what I've said so far. So we had our function f of x here, and the way in which we were approaching trying to find the area between a and b, trying to find the integral between a and b, was to create this cumulative area function. And I was going to create it so that when we evaluated it at the start point for the integral, little a, its value was going to be 0. And it was going to get gradually bigger as you go to the right, and it was going to get gradually bigger and reflect the cumulative area under the curve from A to the point at which you're evaluating the area function. So it gets bigger as the area under the curve gets bigger, so it's a cumulative area function. The other way, it's going to get smaller the more area you've got underneath the curve. So it's going to get smaller by the amount of area underneath the curve from your point to the value a. So as you go to the left, it's going to go down as the area goes up. And that means that it's still a cumulative area function. So if you imagine going to any point here, okay, let's say we go to the point D, then as you go along up this curve, it's getting bigger by the amount of area that you're increasing as you go forward. It's still cumulatively getting bigger as the area under the curve gets bigger. So this is a well-defined thing to create. Now, how are we going to find this function? Well, the thing to think about is what would the derivative of this function be? And of course, the informal intuition of derivatives is that you're making a tiny little change in the x variable, and you're seeing what is the tiny little change that you get in the y variable, and you're imagining that tiny little triangle, and you're just dividing the tiny little change in the y variable by the tiny little change in the x variable. Now, the definition of this cumulative area function means that for a tiny little change in x, the amount by which the area function is going to get bigger is going to be that tiny little rectangle of area by which you are increasing. So what you need to think about is you go forward by a tiny little dx. How big is this area under the curve going to be? Well, as long as dx is infinitesimal, this becomes a rectangle, and the height of that rectangle is simply going to be the value of the function evaluated at x. So that area of that rectangle is just going to be f of x dx. So for a tiny little change dx, the amount by which the area function is going to increase is f of x dx. So we can then write down this equation here. And this is true as long as these are becoming infinitesimal, absolutely tinier than tiny can be. Then we can say that the ratio between them, the gradient dA dx, is then going to just be simply equal to f of x. And that is when we come around to the idea that we need to solve a differential equation. So if we're going to find this area function a of x, we need to find some function, capital F of x, such that when you differentiate it, you get little f of x. So we find an antiderivative, we acknowledge that it is not unique, that you have a whole set of antiderivatives here, so you can add on this constant term here. We need to find the correct one that satisfies this definition here, i.e. that when you evaluate it at little a, you're going to equal 0, because remember, all the other variants here, they're all just the same thing, just translated vertically somewhat. So we want to find the correct one that goes through 0 at the point A. So to do that, what we need to do is say that we want this, when evaluated at A, to equal 0, and that tells us that once we've found an antiderivative, and we've decided we're going to use that one, we need to evaluate it at A and take that value and subtract it off, and then we have our area function here that will go through 0 at the point little a. So, find the antiderivative, capital F of x, evaluate it at little a, subtract that value off, and we've got this cumulative area function that I set out to create. Fantastic. All we need now to do is evaluate it at little b, and that will give us the value of the area between a and b of f of x. And that gives us f of b minus f of a, and there we have the fundamental theorem of calculus proven. Or not proven, but an intuition as to why it works. So I hope that that video has given you some sort of an insight into why reversing differentiation is so closely related to finding the area under the curve. It's because of the way that the area under the curve increases when you think about making infinitesimal increases in dx. Thank you for watching this video. I hope that it's been helpful.